So thanks very much for the opportunity to speak here today. So I'm going to tell you a bit of a story. So a few years back, you'll all remember we had a pandemic. COVID-19, right? Hit us all pretty hard. In New Zealand, well, we're an island nation, right? Middle, or not the middle of the Pacific, down the bottom of the Pacific. And there, we thought we did quite well. What we did was very simple. We shut our borders. And when we shut our borders, that meant nothing could get in and nothing could get out. That's a good idea. At the best of times, getting consumables into New Zealand takes you 3 to 4 weeks, especially if they come by ship. It's a long way, right? Then and after, when there was a crash in the Suez Canal, the ships got messed up, things took a really long time. And that created a big problem for us, because it really demonstrated the fragility of our pipelines, our supply chains. And things like genomic sequencing were not typically done in New Zealand. We did them instead by sending things across to companies in Finland. It's a nice idea, takes 6 weeks. It's not a very good time frame for things that are acute. But New Zealand also has some other issues, or some other unique features, one of which is the Treaty of Waitangi. And so the Treaty of Waitangi cedes sovereignty, or not sovereignty, I shouldn't say that, but it cedes governorship, or kaitiangatanga, the ability to guardians or be guardians of taonga, to the native Māori people. And this is really important because DNA and DNA sequence is of course seen as a taonga, as a treasure. And so we have these issues to deal with. Now, as signatories to the Declaration of the Rights for Indigenous Peoples, New Zealand has signed up to this idea that governorship of that sort of data should be in the hands of the people to whom it belongs. So, the project that we've set up has a very extensive team. We have a governorship and we have a patron, so Dame Rangamarie Ngāti Glavish. We have a governance board who look over the data that we generate. And we have a very large number of investigators and co-investigators without whom this project really wouldn't work. I'm just a pretty face on the end telling you the story. So, despite the fact that New Zealand is a beautiful place, a beautiful environment, a lovely place to live, we do have gene-by-environment interactions that mean that some genomes that we get that recombine and generated when you are conceived do not work in that environment. And those ones, obviously, we have rare disorders. A lot of those rare disorders generate or show or manifest at the point of birth or in the first sort of 96 hours after birth when you are unceremoniously dispatched from your mother's womb. And so in New Zealand, at any one time, we have about 200 children who are in the neonatal intensive care. That's in any one day. We have 5 deaths per 1,000 live births. Now, at least one of those deaths is due to a genetic disorder, is undiagnosed, and occurs in the neonatal intensive care units within the country. So this was a problem that we set about trying to solve. During the pandemic, I actually left New Zealand and I got locked out and wasn't allowed to go back. So I was over here for about 6 weeks. And I visited Matt Luce's lab. And when I visited his lab, I actually saw the Nanopore gear that he had that was running there. We thought, right, this is the way to solve this problem. So I went back and I talked to the clinicians and I said, we're going to do this and we're going to do this with Nanopore and it's going to work a treat. Clinicians looked at me and they weren't very flattering. And they weren't flattering because they'd heard things, they'd seen things. And that's a problem, you know, it's a real thing to deal with. So we devised a solution. And the solution that we devised for the sequencing was this. We have clinical references in. It goes to a multidisciplinary medical team. That team will sort of test to see whether somebody is eligible. If they're eligible, then they move straight through to a consultation for consenting. And we consent trios, mum, dad, and child. The reason we do that is because of the population structure that we have. Māori, Pacifica, their genomes are not well represented in international databases. If we do trios, we overcome those problems. We then take blood from the infant and the parents, 0.5 of a mil. We take it across and we do the sequencing, standard sequencing on the P2s, run that through high accuracy base calling. Then we pop them through Fabric GEM. We get really great results. Bring it back to an MDM, take the results back, get clinical validation. Nice system. Should work. Clinicians thought, yeah, fine. But prove the sequencing works. So the first problem we had was benchmarking. So we had to benchmark. So we were doing precision recall, F1 scores, all computed against truth sets. We used the Genome in a Bottle HG002, 3, 4, 5, 6, 7, so Ashkenazi Jew and Han Chinese. We ran them through exactly the same pipeline for everything else that we were going to use clinically. And then we tested the variance that we got at the end against the truth sets that we had. Doing this, we've been able to show, well, the first problem we had was the chorial DNA. So if you can get that to work, you're halfway to the end of the problem, right? It's not very good, and it blocks up the pores. It's a chronic problem. But we fixed all that, got that working, no problem. We see very nice precision recalls for SNVs and indels. We see them in the high confidence regions. We see them in the coding regions. We see very good SMP calls and small indel calls within the challenging medical relevant genes. So there's about 273 genes that are classified in this grouping. Again, really good. Sequencing depths of greater than 40x do not improve the SNV or small indel detection. SNVs are there, and in fact, that tops out at about 15 times coverage. And the small indels top out at about 40x coverage. The structural variants, we can call those. We can call them in difficult regions. Those calls are, again, very reliable. And we can see very complex CNVs at very, very short time frames. So about an hour sequencing, we can detect these. And when you consider that a microarray to detect these things takes 10 days, even if it's acute, that's a really rapid time difference. But the key thing for us was really doing trios. We wanted to do trios. So we did trios. And the way to accredit this and do this was to compare them to an accredited system. And the accredited system we used was the Victoria Clinical Genetics Service in Australia. They do a short read pipeline, so Illumina sequencing. They do their own calling, their own MDMs. They give us the result. We compare them to ours. This just simply shows the results that we had running through the systems that we had. So there are 6 individuals here. We've done 10 now. But here, what you'll see is that we've got exactly the same calls as from that accredited system every single time. We're novices. These are the first ones that we've done. That's all I'd like to say. What I want to say now, though, and just to finish, is I really want to thank the families that contributed to this study. Those families were under extreme stress at a time when they're watching their loved ones in a situation that no one wants to be in. And I think that as scientists, as clinicians, we owe those people a great deal of thanks. With that, thank you very much for listening.